Hello, we are Team Pac-Man. My name is Andrew Jessup, along with my teammates Andrea Bukuru, Liam Nguyen, and Rashid Ayub. And our two mentors are Dr. Rafael Islam from Cactus Materials, our industry mentor, and Dr. Jennifer Kitchen from Arizona State University, our faculty mentor. The reason why we are building a power amplifier combiner is because of increased interest in millimeter waves for space and telecommunications. High speed and high data rate applications have led to higher demand for technology at high power and frequency. The decreased cost in materials such as gallium nitride and silicon has caused this explosive growth. This project is providing a lower cost option in the market for power amplifiers, transceivers, and other applications. To provide that option, we must develop wafer-level integration of the power amplifier with an operating frequency of 75 gigahertz. We also want a 2-watt output from the power amplifier. In order to get the 2-watt output at 75 gigahertz, we must design a combiner for the power amplifier, which will combine each PA. One PA will give an output of a half a watt and a gain of about 6 decibels. Our plan to achieve this goal is to study the fundamentals, which we did last semester and continue to do today. Learn to navigate the design and fabrication of the power amplifiers using software such as ADS and CST. To do this, we have split into 2 groups. Liam and I are optimizing the design, while Rashid and Andrea plan for fabrication. At this time, Andrea will continue with the design overview.
Thank you, Andrew. This is Andrea Bukuru, and I will talk to you about the design overview. So the goal of a power combiner is to allow for higher power output, which a single PA cannot achieve. And since our goal is to achieve 2 watts at 75 gigahertz, power combining must be employed due to the fact that at higher frequency, there is less power output. So the yellow area on the left figure represents where the combiners will be with respect to the PAs and the output, and that is what our group is focusing on for our senior design project. Okay, so for the design process, we divided our project in 4 parts. The first is pick the type of combiner network, and the second, design and optimize combiner network to meet the specifications. The third is the layout circuit in ADS and have a prototype and cost analysis. And fourth, fabricate design with an order from Cactus Materials. So far, the team has decided to design a Giesel type power combiner design over the previous Wilkinson design. And we have completed the first 2 steps from last semester, and now we're currently on the 3rd and 4th step, optimizing the layout and working on the fabrication to meet the needed specifications. Okay, so since last semester, we have figured our best material for our substrate, and that is gallium nitride. Gallium nitride from this figure has exceptional performance in high frequency and high power applications. And as you can see, we are comparing gallium nitride to other substrates like gallium arsenide and silicon in green and gray. And other materials like gallium arsenide are well suited in high frequency applications, but not for high power applications due to lower breakdown voltage and thermal issues. Okay, so next we're showing our technical work accomplished from last semester. So that is the Wilkinson design, and this is a 2-to-1 power combiner. And we designed it on ADS. And from this design, as you can see in the very middle, is a resistor R1. This resistor is what why we're moving on from this design to Giesel, because it's too big for our layout. but Liam will continue to talk to you more about the GISL design. Thank you.
Thank you, Andrea. My name is Liam Nguyen, and I'm going to talk to you guys about our improved topology design, the GISL. And so the benefits of the GISL over the Wilkinson is that it's easier to implement in the layout since the resistor is not centered in the schematic. The resistor can be placed elsewhere and even farther away, so we don't have to adjust the microstrip lines frequently. Also, since the resistors are grounded, we will suffer less parasitic resistance and less heat dissipation. And since our input terminals, terminals 2 and 3, are perpendicular to our output terminal, terminal 1, we can use less space on the chip and have a smaller chip because the inputs are going to be all around the entire chip. Next, we have the GISL schematic simulation results with the input reflection coefficients and output reflection coefficients side by side in the first and second plot, relatively low, and we can see the inputs for the third and second port are both matching entirely, so we have a symmetrical design. The isolation, the third plot, between terminals 2 and 3 is also relatively low. The transmission coefficient, which is also relatively the most important parameter, perhaps, is negative 3.165, which is a really good number considering negative 3 would be ideal. And the output magnitude is the transmission coefficient, but in terms of watts. So below we can see our calculation of 8 input PAs, each outputting 0.5 watts for each of them, multiplied by our output magnitude of 0.695 would result in our 2.98 watt expected RF output power, which is good because we'll suffer more losses when we do 2D and 3D electromagnetic simulations due to roughness and other parameters. So after that, we have accomplished our customer discovery, which includes reaching out to several different companies and finding out applications for our project. And we figured out that RF power amplifiers and the combiners are used in satellites, base stations, CATV, telecommunications, and many more applications. And potential customers would include space companies such as NASA, SpaceX, and more, military defense companies such as Raytheon, General Dynamics, and more, and of course telecommunication companies such as Samsung, Apple, Qualcomm, LG, etc. Next, we have customer discovery highlights, which include one from General Dynamics, in which they said they operate at 40 to 50 gigahertz, which with over 20 decibel gain for their transceivers, and would be definitely interested in a project such as ours. And Virginia Diodes, which gave insight as to what power and frequency they packaged their combiners for, which include 600 to 700 milliwatts at 130 gigahertz, in which this project could one day evolve to. Afterwards, we went into process variations for our GISL design, which include varying our isolation resistors and terminations separately. Process variation highlights include the isolation resistors being varied at a maximum insertion loss of 0.001 decibels at negative 10%, while varying the terminations. For the input terminations at negative 10%, we suffered a maximum insertion loss increase of 0.001 decibels, and for a plus 10% input termination variation, we had a maximum insertion loss decrease of 0.059 decibels. And for the output terminations at negative 10%, we suffered a maximum insertion loss decrease of 0.059 decibels, and a maximum insertion loss increase of 0.088 decibels occurred for the output termination at plus 10%. And these results are anticipated because for the output termination, it acts as a load. And so when we lower our load impedance, we'll have more throughput, meaning less reflection. And so this agrees with the reflection coefficient theory. And also for the input terminations, since they act as a generator, their results are expected to be the inverse of that of the load. Next, I will turn it over to Rashid, who will talk about the final simplified product.
Thank you, Liam. My name is Rashid Ayub. In this slide, I wanted to explain the final and simplified version of our project. This is the high-level schematic of our project. As this picture is showing, we do have a total of 8 power combiner consists of diesel-type combiner, and a total of 8 input and 1 single-ended output. Each combiner consists of 2 standard intrinsic impedance of 50 ohm. Again, the goal is to get 2 watt as an output power at 75 gigahertz. In the next slide, I wanted to take the time to talk about the rectangular waveguide circuits. We decided to design this type of circuit for many reasons, but the most important reason is that the waveguide circuit is less lossy at high frequency. Also, it can handle high power capability. We are going to use a transfer mode TE10 and a waveguide size of WR12. That would allow us to operate in a range of 65 to 96 gigahertz. The ultimate goal is to design a Y-junction on CSC software that is similar to the Giesel combiner. Some of the future work as we approach towards the end of the semester will be as follows. First, finishing up the Giesel combiner and optimizing the layout, performing all possible analysis, and simulating the design in ADS to see the losses and the output power. Finally, finish up the Y-junction design on CST and using it 4 times to combine the 8 power combiner to a single-ended output. Some of the challenging that our team faces are: first, familiarize ourselves with CST to design the Y-junction waveguide circuits, finishing up and optimizing the Giesel design and its layout, calculating all the S parameters for the Y-junction to be able to do the 3 steps transformers. Finally, performing 2D and 3D electromagnetic simulation for Giesel layout. To recap, the goal for this project is to design a power combiner that combines 8 power amplifier into a single-ended output, getting 2 watt as an output power at 75 gigahertz. The team will focus on designing the Giesel power combiner on ADS and performing electromagnetic simulation. Lastly, prepare for the demo day and get the prototype and the simulation result from ADS and CST as proven for meeting the project specification. That concludes our presentation. Thank you all for listening.